Hey guys, this is Mr. Allen, and I'm going to do a video here on the Pythagorean Theorem. I'm going to try to keep this to about 10 minutes. So our objective here is to just use the Pythagorean Theorem and its converse. We kind of already have mentioned this Pythagorean Theorem, but this will be kind of the formal notes, if you will. So the Pythagorean Theorem says that in a right triangle, the squares of the lengths of the hypotenuse is equal to the sum of the squares of the lengths of the legs, or c squared equals a squared plus b squared. And I know normally you hear the Pythagorean theorem is a squared plus b squared equals c squared. That is fine to do that, but we're going to write it with the c squared first on the left. There's a reason for that I'll explain later. So I'd like you to note that if it were my definition, I'm using the one out of the book. If it was my definition, I would write it more as an if-then statement, and that if-then statement would look something like this. If it's a right triangle, then c squared is equal to a squared plus b squared. So we've talked about if-then statements, conditional statements. So first thing you got to do, the condition for the Pythagorean theorem to work is that it's a right triangle. Another thing I'd like to mention is something called Pythagorean triples. So a Pythagorean triple is just three numbers that satisfy the Pythagorean theorem. So here you'll see, I got this off of Wikipedia. It says a squared plus b squared is equal to c squared. And so, for example, 3, 4, 5 is an example of a Pythagorean triple because 3 squared plus 4 squared is indeed equal to 5 squared. Here is a list of the first several dozen Pythagorean triples. So you can see the 3, 4, 5. You could also write it as 4, 3, 5. But like, for example, another one is, well, let's just look at one, 27, 36, and 45. So 27 squared plus 36 squared is equal to 45 squared. So here's our first example. So we've got triangle ABC over here. It's a right triangle. They want us to find the length of the hypotenuse, and they also want to know if the sides make a Pythagorean triple. So let's go ahead and run through that. So first thing was we want to know that the segment AB, it's the hypotenuse because it's the side opposite the right angle, or the longest side, if you will. So then we can just use our Pythagorean theorem, which is c squared equals a squared plus b squared. And in our case here, it's going to be the length of AB squared equals length of AC squared plus BC squared. And then we can substitute those measures in, 20 and 21. Then we're going to square them. So 400 plus 441, which is 841. And now to get rid of this squared, we do plus or minus the square root. When we do the square root of this 841, we get plus or minus 29. Now we really only need to worry about the positive number here because we're talking about the actual measure. You're not going to have a negative 29 length. So therefore, AB is 29. The hypotenuse is 29 in length. The sides then are 20, 21, and 29, and thus they represent a Pythagorean triple since they're all integers. So that wraps up example 1. Example 2, we've got another triangle, but notice now, instead of us needing to find the hypotenuse, we're going to have to find one of the legs. Here it says to express our answer in simplified radical form, so that's the reason I'm throwing this example in here. So again, we're going to do the Pythagorean theorem. We're going to substitute 20, though, in for C because we know the hypotenuse length. And I just left this length here for A, and then the other leg is 8. So we square, then we subtract the 64 over to the other side, and then you take 400 minus 64, which is 336. And again, we're just going to deal with the principal root here of 336 in it. Here's the part that you're probably going to need a little refreshing from Algebra 1. It turns out that 336 is equivalent to 16 times 21. 16 is the largest perfect square that divides evenly into 336. And so then you can break the radical into the square root of 16 times the square root of 21. And so the final answer here is 4 square roots of 21. That's the value of x. I'd like to make a note that 4 square roots of 21 is approximately 18.33, which is not an integer. So this is an example of 3 lengths that are not Pythagorean triples. Okay, now this is the new stuff for the lesson today, and It's the converse of the Pythagorean theorem. And we already mentioned the Pythagorean theorem. So the converse, remember the converse, what do we do? So if we got P arrow Q, the converse means we take the P and the Q and we switch them around. And so what this converse is saying is if you square the longest side of a triangle and it's equal to the sum of the squares of the other two sides, then it has to be a right triangle. So we've switched it around, the condition and the conclusion. So here's a couple of examples. I'm going to just kind of show you the work on these very quickly. So we got this triangle here. Certainly looks like a right triangle. Let's see if it is. Now notice this square root of 13, or square root of 113, that's the longest side because the square root of 113 is over 10. So that's the hypotenuse. That's important for you to notice that that's the hypotenuse. So then we plug that in. So we got our c squared equals a squared plus b squared. We work it out. So when you square the square root goes away. And then, of course, 7 squared is 49, 8 squared is 64, 113 equals 100. So therefore, even though we didn't have the measure shown to be a right angle, it turns out that that is indeed a right angle, and therefore that is a right triangle by the converse of the Pythagorean theorem. B here, again, I'm just going to show the work right here. This one, when you work it out, you get 1,020 doesn't equal 1,521. It's really close. It looks like it's a right triangle, but this one is not a right triangle because it does not satisfy the converse of the Pythagorean theorem. Okay, so here's our last theorem for the day. This is the Pythagorean inequality theorem. So this is a kind of a more general result from the converse of the Pythagorean theorem. And it basically, and this is why we write instead of writing a squared plus b squared equals c squared, we write the c squared part on the left. It turns out that when you work out this inequality, when you work out the longest side squared and then the other side you put a squared plus b squared, so the longest side, if it's a right triangle, is the hypotenuse. It turns out if this inequality is less than, then the triangle is acute. And if it turns out it's greater than, then the triangle is obtuse. So here we've got an acute triangle, and here we've got an obtuse triangle. So let's just see that in an example. So here's one where there's no picture, so you may have no idea what kind of triangle it is. We don't know if it's acute, obtuse, or right. So we're going to try to figure that out and explain it. So the first thing you want to do is identify that the hypotenuse here, well, it's got to be the biggest number. The longest side has to be the hypotenuse, so 14 is going to be C. And so we're going to plug 6 and 11 in for the other two things. And notice here I wrote c squared equals a squared plus b squared. That's the Pythagorean theorem. But now I've changed my equal sign, or my equal signs to question marks because we don't know the equality exists there. So remember, c is 14, so I put 14 in for that. I let 6 be the A and then 11 be the B, and then I work it out. And it turns out that you get 196 on the left of the equal sign and 157 on the right, which means this inequality symbol is going to be greater than, because 196 is greater than 157. That means that c squared is greater than a squared plus b squared. So if we go back and then we look at our Pythagorean inequality theorem, we can now conclude that this is an obtuse triangle. It's an obtuse triangle. So that's it. That's it for the notes, and I hope that was brief enough for you. Please feel free to rewatch this or slow it down or skip ahead when you rewatch, and you can focus on anything you might need to know on section 9.1. Thank you very much.